Hello and welcome everyone to today's Space Elevator presented by the International Space Elevator Consortium and presented by Dr. Peter A. Swan. He is the president of the International Space Elevator Consortium, and as such he leads a team who furthered the concept with incremental studies and yearly conferences. Pete received his PhD from the University of California at Los Angeles in mechanical engineering with a specialty in space systems. He is currently an adjunct professor at Arizona State University. And with that, I'm going to show you Pete's lovely face here, and we have a quick poll that we would like you to participate in, and it's right there on your screen. Have you heard of Galactic Harbours? And we'll just take a few minutes to let everyone vote there. Okay, well, it looks like nearly everyone has voted, so it's a pretty even split, 51.7% to 48.2%. So that's very interesting. So right now, I'm going to now turn everything over to Dr. Peter Swan.
I'll continue it. It turns out that most of the time when I have lectures or education or something, I have to first take a few minutes to explain where your fire exits are in the bathrooms. But I'm going to transfer that responsibility to each of you, so we don't have to worry about that today. Okay, welcome to a start of something exciting. Space elevators, galactic harbors, and the future. What I'd like you to do is think big. This is a mega project. This will open up the solar system. And here's the key part. You can be a part of it. Dream about what can be is another request from me. And the other one is recognize that space elevators are compatible and complementary to rockets. For you that do not know me, I'd like to just summarize real quickly that I have over 50 years working in space systems. Most of them were mega projects, so I can really say truly that I've been there and done that. The International Space Elevator Consortium has only been around for 12 years, but it has developed a remarkably large body of knowledge on space elevators. And most of it can be downloaded from our website in PDF on the study reports. This webinar is the start of a series of extraordinarily important topics on space elevator developments. The next one is 29 May. It's called Graphene, the last piece of the puzzle with a question mark. Now, just to give you a little background before we start the charts, we have some basic thrust inside the space elevator community and ISAC specifically, and we've come to a conclusion that one, space elevators are closer than you think. The second point is space elevators are maturing into the Galactic Harbour, and we'll go into that quite a lot here during the discussion. The third point is recent research at the Arizona State University has resulted in three strengths that are being emphasized. They were known before, but they really haven't fallen into their own. And they are fast transit for interplanetary. Let me give you an example. ASU has shown that you can get to Mars in 61 days. Wait a minute. The normal is 7 to 9 months. This is 61 days. Now that's just a few times a year, and then the rest of the times they're a little longer than that. But they've shown fast transit and fuel economy approaches. So they've got optimum times and days to release. The second point is the space elevator can release the payloads going to Mars every day of the year. There is no 26-month wait till the next launch window. Now, the beautiful thing is right now, our launch window to Mars is this summer. And we've got like 3 missions to Mars planned. But the point is, you have to wait 26 months to get to the next window. Space elevators can launch daily. And then also, because it's an infrastructure, a permanent infrastructure, it can launch, release at the end, massive payloads of cargo. So the 3 major points are fast transit, daily, and massive. This leads to the conclusion that I have out of this Interplanetary Missions Support study, which will be published sometime in June, that Galactic Harbours will enable movement off planet and will be essential to interplanetary mission support. Now, 1 or 2 other items. The space elevators are ready to start developmental engineering testing. We're going to talk about that in this testing section. And we need to work with everybody around the community to show how Galactic Harbours are complementary to the rocket programs. Now, I have been aware and working on space elevators for 37 years. But I now realize that space elevators are essential for the future of humanity. That is why I'm here. Okay, now we're going to start a little bit on the charts and go through the process. But first, let's think about last year. Last year, we had some major breakout items. We finished the International Academy of Astronautics study, and they came up with the answer that we really can mature from space elevators to Galactic Harbours. We've shown that we don't have to wish for a material anymore. We have single crystal graphene in the laboratory. The good news is we have many other materials that are the same type, 2-dimensional, and they might work also. We've gone from an immature plan to one where we have a preliminary positive assessment on each system segment technology. We believe we're ready to go into major segment testing. So as one friend of mine, Michael Fitzgerald, has recently said, the story is still being written. Of course it is. It's a mega project. The apex anchor is where the Galactic Harbour meets the shoreline of outer space. I love that concept. We're on the shoreline at the apex anchor. And then the other one is the transportation story of the 21st century is going to meet the final frontier. Okay, well, what's going on this year? Oh, we have some great things going on. NASA contracts and expectations are to go to the moon in 2024 to 2028. But recently, our Congress has stated we not only want to go to the moon, but we want to go to Mars. So that means engineering planning has to take into account both on the types of vehicles, etc. Now, that's just NASA. I put that up there because those are recent things. European Space Agency, the Chinese, the Indians, the Russians, and I don't want to forget anybody, but almost everybody is planning on moving off planet and going to at least the moon right now. There's also, in parallel, a tremendous activity on commercial plans. In fact, today I just read that Blue Origin and SpaceX, and I apologize, I've forgotten who the third winner was. There were 3 winners today from NASA to build the landers that are going to take our people to the surface of the moon in 2024 to 2028. That awarded was just to today. So the commercial, and that's a commercial product. It's not a government source contract. It's commercially provided. Boeing and SpaceX are going to the International Space Station with people this summer. SpaceX has it scheduled on May 27th. In addition, we have a contract to deliver to the surface of the moon, just product, by Maston, and SpaceX has another contract to deliver to the Gateway. But the important thing is not the details, but the point that there are tremendous commercial thrusts going to the moon and Mars. So humanity is moving off planet in a big way. What are we going to talk about today? We're going to kind of expand on what a Galactic Harbour is. Then we're going to talk about where the status of Tether material is. And we're going to talk about where engineering development is. Then we're going to focus on the mission called Interplanetary. I love that. We're just finishing up a study. We've got some great inputs from Arizona State University. It's a neat place to be. So, what's going on in the future? Well, the answer is all the normal geosynchronous space stuff is going on, and there'll be revolutionary missions after that. We have refueling and repair of ailing satellites. We have construction of satellite systems at geosynchronous. Those will be revolutionary ideas. There'll be huge growth when we can get payloads to geosynchronous inexpensively, daily, and with a lot of mass. The lunar and interplanetary missions have been kicked off around the world, and human exploration will occur. We are going to the moon and Mars. Okay, the 2014 International Academy of Astronautics study had about 40 global space experts, and we did a report on space elevator feasibility. Well, along the way, we kind of looked at demand for missions. So we kind of sized out what the missions were to be in the future that the space elevator should support. Well, those are huge numbers, and those are metric tons per year of needed mass. Now, that was done in 2014. That does not include the NASA Artemis program nor the SpaceX Let's Go to Mars colony issue or anything else. Those are numbers that are about 6 years old. So what we did in our interplanetary mission support in ISAC is we chose 3 missions to be reference missions, destinations that we can define. I talked with a friend of mine who's running the space solar power activities, and he came up with the answer to to supply electricity to 12% of the human population in 2060. He needs to have 5 million metric tons of geo. Now you can divide that by 100 metric tons, which is Elon Musk's SpaceX, and figure out how many launches that is. The SpaceX colony on Mars has been quoted as needing 1 million metric tons. And the Moon Village, which is an emphasis going on right now in international activity, would need something like 500,000 metric tons. If you divide that by, a current rocket, it can't be done. Any one of those can't be done. But the future rockets are going to provide significant improvements, but they still can't do the job. We need space elevators to provide a permanent infrastructure that will supply mass to these locations. If we look at the research at ASU, it was done by Professor Matthew Peet, and then one of the lead engineers, the lead, was James Torla, and about 8 or 9 or 10 other students studied the rapid transit to Mars from the tip of a space elevator. So if you go up 100,000 kilometer altitude and are released from there during the rotation, you can get a velocity of 7.76 kilometers per second. So you're leaving the sphere of the influence of the Earth going very rapidly versus the release by rockets of less than 3 kilometers per second. So we're well over 2 times what they can provide. So we can get to Mars in 61 days, a few times in the 26-month cycle. We can lift massive amounts. There's some numbers for you. We're going to show all those numbers in our study report. But if you think about it, 79 metric tons per day per space elevator is a lot of stuff per year. Now, if we look at daily departures, oh man, that's a neat concept. We can go to Mars releasing every day. Now, if you're on Mars and need a hammer, you really don't care whether it was sent 61 days ago or 400 days ago, so long as it's there when you need it. So the schedule is it varies a lot depending on when you release it in the orbital dance of the 2 planets. But the point is we can ship stuff just like a logistics train. And then, of course, we can launch every day from our activities. So those are the new results from the Space Elevator Interplanetary Mission Support. Here's what a galactic harbor is. We've come to the conclusion that once we get movement of payloads, there's going to be a lot of business that accompanies it. There will be enterprise along the way. So what we thought is we'd put two space elevators close together. Now, if you're a commercial venture building the first space elevator, the first thing you want to do is put a second one up so you can make sure that you don't get captured by that silly thing called gravity again. So it's logical to have two space elevators close to each other as one commercial venture. We're calling that a galactic harbor. It's a unifying vision of mission and enterprise. Here's what the Earthport area would look like. Now, these numbers are just guessed at right now, but if we separated the two tethers by 40 kilometers, we could have an activity there with one as principal up motion and one up motion, but with some coming down. So we have two tethers in a commercial venture called the Galactic Harbour. Halfway up, or less than halfway, but somewhere up there, at the geosynchronous altitude, we have a very, very beneficial area. It's called the geosynchronous arc. There is a lot of business going on up there now on the commercial and the government side. And if we can supply payloads inexpensively to that area, the region will blossom as a commercial enterprise region. It's going to have very much growth in things like repair of satellites, refueling, construction, new missions, all kinds of things in that region. And then we go to the top, which is called the apex anchor. This provides us a horizontal velocity that is tremendous where we can release. An example, if we get to the apex anchor, we can get to the moon in 14 hours. Now, it takes you 2 weeks to get to the apex anchor, so it's just an aspect that you're going so fast when you release, you can get to the moon in 14 hours. That gives you a feel for what we're talking about. The Galactic Harbour architecture is one where we're going to combine the space elevator transportation system with the essential business development arena that'll occur throughout that whole area. This is a 21st century concept. We're going to have an infrastructure, and along that infrastructure, we're going to have tremendous business development. We have a vision of galactic harbors, and we just start with 3 of them. 3 galactic harbors, 2 space elevators per. And that would give us enough capability to do 30,000 metric tons a year at the beginning with the minimal space elevator. When the space elevator graduates to its full operational capability, somewhere around 80 metric tons, we would be doing 173,000 metric tons a year of transportation. Now, it turns out currently we're doing about 1,000 metric tons a year, somewhere around there. Pick any number you want, but certainly not in the 100,000 kilometers, 100,000 metric ton region. So what are the strengths of these galactic harbors we've defined? Well, if you think permanent infrastructure, it all falls in place. Routine, daily, revolutionarily inexpensive, flexibility for cargo, environmentally friendly, all those things that come with permanent infrastructure. And then when we start thinking about interplanetary missions, we're talking about we are going to enable these missions. We can move the mass required for Mars, Moon, and space solar power. So we're going to enable missions. That's a remarkable statement. I think we just skipped one here. Okay, agenda. So where is the space elevator today? We're going to talk about 2 of the issues, tether material and engineering development. But first, what is the case for space elevators? Well, we've been talking around it, but basically it's a permanent infrastructure. It's daily activity with rapid transit. It's environmentally friendly, and we believe the material for the tether is here today. So we believe that space elevators are real now. I mentioned earlier that ISIC has provided a remarkable body of knowledge on space elevators. And if you go to our website, you can look at 10 studies that we've accomplished over the last 12 years that address major issues. So you can go wander around, see what your favorite topic is, and download. Well, in addition, we have two more ongoing. I've mentioned the Interplanetary Missions Support one, which we're hoping to publish in the June time period. But we're also doing one called Beneficial Environmental Impacts of Space Elevators. So that's twofold. One is if you have an infrastructure, you don't have to do a lot of burning fuels in the atmosphere. And the second is that we're going to enable missions that would be beneficially good for the Earth's environment. We're going to go into that a lot, so you can watch that. In addition, there's been two International Academy of Astronautics studies that were accomplished. 2014 showed that the concept is feasible. And in 2019, we developed a road to where we can follow to get to a space elevator era. We really looked at the technologies hard in there. Now, in parallel, the Obayashi Corporation has done an internal study looking at how do you build a space elevator. They did an excellent job. Their requirements were for massive movement to geosynchronous. So their solution is a little different than the IAA or the ISIC one. All very compatible, all parallel. It's just a little difference in requirements at the beginning of the study. The 2013 study has been enhanced by papers by members of that team over the years, and it's very compatible with the ISIC approach. So the IAA, the Obayashi, the ISIC studies have really taken the space elevators a long way in this century. Okay, the next part is the graphene. Now, thank you, Adrian. He's in the audience, so I have to thank him here. I've used a few of his charts, and the real question is, what are we really looking at? Now, I'm going to just cover this quickly, and Adrian is going to spend a whole hour on this at the end of May. There's a whole new family of types of graphene in the carbon family, and it's called 2D materials. Now, the beautiful thing is that this is in the laboratory and it's real. The complexity is that we really are at the beginning of the development of this, and we have a long way to go. But we have some really good ideas. It's shown that it can work, and it really is under development. Now, just an aside, and I'm not an expert in this area, but there are other atoms that work in a similar manner to carbon, like boron nitride will work in a similar manner. So it's not just a carbon graphene approach, it's also some other materials. But the concept is that we'll have a way to create a single level, single atom thick sheet of carbon atoms bonded through the atomic approach for the molecular approach, yielding extremely strong tensile strength. And then Adrian Nixon has come up with an idea of how we can pull the material out of the furnace so that it's a continuous process and we can reel up the graphene. This is very important so we can have long stretches of it. Here's a little Tether candidate materials. Those are historic materials, and these are the newest ones in the last 15, 20 years, carbon nanotubes, boron nitride tubes, and then the graphene fits right over the top. That type of capability will be long enough and strong enough for tether materials, for space elevators. So yes, graphene is strong enough for our candidate tether material. Here's an idea that Adrian came up with on how we would assemble it in orbit. And then we would just pull off the reels, combine the multi-layer graphene tether, and let it flow down toward the Earth for our full tether deployment. Is the tether feasible if it's made from single crystal graphene? Well, there are some little points there and everything else. But the bottom line is, yes. Whoops, sorry about that. I hit the button twice. The answer is yes. We can do it within our lifetime. Now, the good news is the people that made this chart or over teenage years. So our lifetimes are not as long as people worry about. So it should happen in the next few years, next 10 years or so. Now looking at the engineering development, the International Academy of Astronautics did a very good study, 4-year study. The International Space Elevator Consortium did 4 or 5 individual year-long studies, and they've came up with the statement that we're ready to leave the technological feasibility questionable box and move into the engineering validation testing arena. Now, this layout of 4 boxes to develop a big engineering project is one of many proven approaches. Depends on which country you're from, which company you're from, which program management school you're from, but they all boil down to these 4 major topics. The studies we've conducted show that each of our major segments for the space elevator are ready to start doing engineering testing and move into that next box, which is called engineering validation. Here's 2 pages to summarize those, and you can read the document, IAA number 2 book, and you can get the details on TRL, technology readiness levels, and status of the different materials, but I'll go over these quickly. The first is Galactic Harbour Earthport is ready to be developed. This can be done, and we can see that being one of the first things we develop as an example of progress in space elevators. The Op Center, we can do that today. We have many space operation centers, many operation center for transportation infrastructure. We know how to do that. I'm not saying it's easy. It's going to be a very complex problem to keep track of everything and have knowledge of everything in its process. The Tether climber is definitely a challenge. We have to understand the wheels. I mean, the wheels are going to turn a lot to go 100,000 kilometers. We know that they're going to have wear and tear and bending and reliability. We've got a lot of issues with the Tether. One of the big ones is we're not really sure of the friction coefficient of this new material. So if we don't know the friction coefficient, boy, we've got to really worry about how this is going to work. But those are questions we need to answer in the testing game, and we need to move to that. The GeoNode is a very beautiful area with a lot of experience, with a lot of people. We're going to put a tether in the middle of it, so we have a lot of questions we have to deal with, but it's doable. Okay, the apex anchor. Well, nobody's ever done one of these, so there's some good engineering challenges here. I love it because I have been focusing on the apex anchor for about 5, 6 years. The first thing you have to understand on an apex anchor is it is very complex in the sense of dynamics of the tether. We must be able to exercise the apex anchor to moderate the motion of the tether. Now, when I say exercise the apex anchor, the obvious answer is a little thruster up there, but of course we're going to run out of fuel, so we'd have to bring more fuel up. But also you can reel in and reel out, and that dynamic motion will affect the dynamics of the tether. So we do have ways to moderate the dynamics of the tether using the apex anchor. The tether material, we've talked about that a little bit. The prime material is available. We've got it. We have to develop it now. And of course, much testing in that arena has to occur. Now, assured survivability. Everybody asks the questions about space debris. The answer is ISAC has done 2 studies, one in 2010 and then one just updated in 2020. In the 2020 version, we projected to the density of debris that should be available or should be there in 2030 with these new constellations. So literally, we asked NASA how many pieces of debris and spacecraft would be in orbit in 2030, and they had an answer for us. So we use those answers for probability of conjunction. And when we looked at those, the answer is space elevators can live and thrive in the debris environment of 2030. It's a management and operations issue, and you have to design the tether to take care of little things like small hits and move out of the way for the motion to get out of the way of the big things. The beautiful thing is in 15, 18 years, we're going to have a heck of a computational capability around the globe, tracking all the debris and projecting 24 hours, 48 hours, 72 hours ahead for where each piece would be. So assured survivability, I believe, is a topic that we have under control, but has to be continuously developed. The next steps. Space elevator community needs to be in discussions around the world on how do we approach movement off planet, interplanetary missions, and robust operations of geosynchronous. The other thing is we believe we ought to create a Space Elevator Institute where we can address these issues. We can address the topics of importance at the time and look at the future. There are two major thrusts right now. How do we set up a baseline transportation infrastructure? And the other one is individual topics. A lot of issues, one of which is the material issue, and we have to study that. And if we had a Space Elevator Institute, we could really start addressing some of these major issues. Okay, what's the status as of today? The answer is the material is ready for development. We need to develop it. We need to test it. We need to figure out how to manufacture it. We need to figure out how to deploy it at geosynchronous. We're ready to move into that second blue box in the developmental phase, which is essentially building and testing the major segments of the space elevator. We're ready to join the major discussions around the community, and we need a Space Elevator Institute. Okay, now we're going to get into the fun one, and I'm going to have to go through this fast since I only have about 7 minutes left. But the beautiful thing is we're going to have a report out in about 60 days. Okay, this is a pretty picture of the dance of the planets, the Earth and Mars going around. Position one equates, and then Earth and Mars goes around. So you can see where they are in position 1, and then position 2, and position 3. And you notice that Mars takes about 26 months to go around that whole thing. Okay, so we go to the next one. Oops, once again, I hit it twice. This is a traditional approach for Hohmann transfers. Why do we use Hohmann transfers to go to Mars and other planets? The answer is minimum energy. So therefore, if you're using rocket, you have to do minimum energy transfer because it's the only thing we can do. If instead we have 3 times the energy at release, we can do something different. So the answer is we want to do something different than tradition, something different than a Hohmann transfer. So what we want to do is provide a capability where we can get there faster, means we got to go fast, move a lot of stuff, and do it every day. So the way to do that is come up with a interplanetary missions architecture that'll provide those characteristics. And we have to remember there's a demand pull. Why are we doing this? And the answer is humanity is moving off planet for one, but we also have the Moon Village being developed, SpaceX's colony on Mars, and then there's always the environmentally beneficial movement of having electrical power shipped down from geosynchronous to any place on the planet, and that's space solar power. So what we need is a cooperative architecture working together, rockets and galactic harbors. Remember our needs here, those 3 needs, and those are verifiable numbers. Then we look at the new paradigm. If we leave from our rapid approach, we can really do it with fast transit, everyday releases, and massive support. How do we do that? Well, we go the end of a long line. We rotate that line very fast, and the tip is going fast. So you can see at 100,000 kilometers altitude, we're going 7.76 kilometers when we release from the tether. Here's the way it works. If you're going to Mars and you do the Hohmann transfer, your release from the rockets would be in the same vector as the Earth's velocity. All you're doing is adding velocity in a vector addition in parallel. So that way you get to Mars, you leave at the perigee of an ellipse and you arrive at the apogee of an ellipse. But if you have extra velocity, you can shortcut. So what you do is you don't leave in parallel with the Earth's velocity. You're leaving with an exit velocity off of the parallel. So what we're going to do is leave at a different angle and cut the corner. So you can see that if you don't do the Hohmann transfer and you cut the corner, you can do it in like 61 days. Here's a whole bunch of other alternatives. I said you could leave every day of the year. Well, this shows that you leave it every day of the year and you might hit it at a different time. If you look at the lower left, we didn't hit Mars on the first time across the Mars orbit. We hit it coming back. The answer is, with velocity, we have a lot of choices. Here's a chart from the students that did the work at Arizona State University. The beautiful thing there is he optimized time of flight and delta V, amount of fuel needed to slow down at the other end. And he's had a whole bunch of cases where they're optimized. Now here's a kicker. If you want to go from Phoenix to LA, you got to find a bus schedule and go that way. Well, with a permanent infrastructure and release every day, we developed a bus schedule going to Mars. Now that's an interesting concept. Bus schedule to Mars. Okay, I'm going to skip this one real fast, but just one line I'd like you to look at. When Saturn V went to the moon and dropped off the people, it deposited on the surface of the moon 0.5% of the mass on the pad. That means you used up 99.5% of the mass to deposit something on the surface of the moon. If you use permanent infrastructure, a la space elevators, you can do a heck of a lot better than that. And you don't throw anything away. Massive movement, single tether, 100,000 kilometer long. Initially, we're going to do 14 metric tons. Over time, we'll move up to 78 metric tons. Over time, we'll end up with Galactic Harbours with 2 space elevators. So you can see the numbers are coming together pretty good. This one's a hard chart to do. You can look at it later. By the way, you can download the charts. Karen's going to provide that. This summarizes it right here. For the 3 reference missions that are demand pull on the engineering sense, we looked at how long it would take to fulfill the needs if we did each one of these activities. Well, at IOC, with only 14 metric tons per spacecraft times 2 space elevators times 3 galactic harbors, we could do Mars colony in 33 years and Moon Village in 17. But to do space solar power, it'd take 150 years. Oh, bummer. But as the Galactic Harbour matures and we get better material and we have 2 tethers versus 1 tether, et cetera, et cetera, et cetera, as the space elevators mature, we'll move up to 79 metric tons per space elevator. So that'd be 2 times 79 times 3 galactic harbors, 365 days. We can supply Elon Musk colony in 6 years. The transportation infrastructure is the key, permanent infrastructure. So our conclusions are pretty straightforward. We need a family of space elevators for all the different missions. And we would like to have a vision of space elevators that develops the business entrepreneurial side of that arena. We recognize that we're going to have strength as Galactic Harbours that will move to enabling new missions. So we really need to initiate the space elevator program soonest. So we've always come up with a space elevator is closer than you think. We need to link the space elevator transportation system to the space elevator enterprise, which then provides a unifying vision of galactic harbors. And of course, I'm going to leave you with this chart, which is a fun one. The apex anchor is where the shoreline of outer space starts. And the transportation story of the 21st century meets the final frontier. So we have finished on time. So Karen, how do you want to do this? We're going to have a poll first?
Sure thing. Here we go. I just want to get your opinion on this. Space elevators? Which is first? Do we go up to the Earth, from the Moon, or Mars?
That's a pretty good number of people.
Okay, a good chunk of people have answered. And shall we show it to everybody, Pete?
Oh yeah, show it to everybody. That'd be good.
All right, there you go. So now everyone can see the results.
Okay, the bottom line is I love the results because they agree with my idea. No, the kicker is there's no right answer. I just thought we'd give a poll here. My philosophy is we need to do the Earth space elevators so we open up off-planet movement. The opening up of off-planet movement would then enable elevators at the Moon and Mars and on asteroids and wherever else. Space elevators will be used elsewhere besides the Earth, but we really need to move people off planet first. That's my feeling. It's not the only answer. There are other answers, but that's my feeling. Okay, Karen, how do we want to do these question and answers? Okay, I see one question that is there an update to the space elevator study of 2010? Yes, it's called the 2020 study. It's on the site. You can download it.
Okay, I'm sorry, I was muted. So I put the presentation as a PDF in the center of your screen. You just need to click it and then you can download that file and you'll have it to look at and reference. And then there were some things that you did talk about, Pete, but there were some other questions. Couldn't the space elevator have huge positive impacts if working with the ISS?
Okay, here's my answer. The answer is the ISS is doing a great job, but space elevators in concept don't work well in low Earth orbit. We're in the equatorial plane at high velocity. When we release from that, we're going to stay in the equatorial plane unless we use a lot of fuel. So the ISS is somewhere up around, what, 48-degree inclination or something like 50-degree inclination, something like that. So it takes a lot of fuel to get from our low Earth orbit, low inclination to high inclination. So our space elevators have some strengths in low Earth orbit, but they don't have the flexibility of the rockets. That's why I believe rockets and space elevators are compatible and complementary.
Okay, and there's another question regarding debris conference. Is there some progress, like the first International Orbital Debris Conference, which was held December 2019?
Yes, I have been keeping track of orbital debris since I was a young captain in the Air Force tracking orbital debris in what's now the Space Force. Um, and space debris is one of my little hobbies. I helped write the 2010 report and the 2020 report, and I've been going to orbital debris conferences over the years, and the guys down at Houston have a very good record of really doing a lot of good work. And around the world, I actually came up with a statement about 10 years ago in the international community that there should be no debris created in the debris zone. So instead of saying everybody could do a little bit, I came up with a zero debris tolerance statement. And it was alive for probably 3 years in the international community, and nobody wanted to buy into it, so it kind of died. But yes, space debris is one that we must pay attention to and help. And I encourage anybody to figure out how to take it out of the orbit. Jerome Pearson is a leader in that area and has done some really, really good work, and we work with him and that type of stuff.
And then as a follow-up or in addition to, in regards to debris, is there a possible solution to mitigate the degradation of the tether due to the LEO and MEO debris?
We have lots of ideas in that. We talk about that in the 2020 and 2010 support. One of the things is we believe that all tether climbers will have inspection capability on the front or back of the little climber. And so we will be monitoring the tether daily on, holes. You also design the tether so it's curved so that a larger piece, if it were to randomly hit, wouldn't sever it, it would just blow through. And so we've got all kinds of discussions on space debris. The only debris we're really worried about is in LEO, and the MEO is there, but not that much. We can move out of the way of that easy. In GEO, it's all going relatively slowly, so we'll see it coming and move out of the way. The LEO stuff, we really have to have the capability to absorb some impact. Now, the Houston guys do really, really good work and have a lot of studies on impact effect, going at 17,000 miles an hour times 2, if you go in the opposite direction. The impact of small material is quite explosive on the material when it hits. So they've done a marvelous amount of job. We must translate what they have done, the impact of space debris parts, small parts, on, let's say, single crystal graphene. We don't know the answers to that. That's a whole steady area we have to look at. There's no doubt about it. There's a lot of work in that area.
All right, great. And I have two questions here about the tether, so I'm going to kind of combine them. First, what is the development or their development, I'm not sure who there is, on the tether climber? And how do we get the first tether up or down, depending on how you want to look at it?
Okay, that's a thing. If you move that little blue chart there with or make it smaller, the one on the file, the backup chart is the one that really shows that. The way we deploy the initial space elevator is we take rockets up to GEO, and then you have the center of mass at GEO, so it's staying above a stationary point on the Earth's equator. Then you deploy the tether down, and you have to deploy it up, so the center of mass stays at the location above the Earth's equator. And then you deploy the more tether down and more tether up, et cetera, until you can grab the tether at the bottom, pull it on, anchor it to your Earth port. Once you've done that, then you take the upper tether and deploy more tether out and make it go beyond what would be an equal number. So there literally is tension up at all times. And then you get a stable position. We've come to 100,000 kilometers as a fallback position. And at that point, you now have enough tension in the tether such that when you put a tether climber on it and it climbs, it doesn't pull it down and stretch it, and you have a bunch of tether on the ground. So we've done a lot of studies on how you do that, but the process is pretty straightforward. There's a technical note in the architecture portion of the website that goes into the sequences of how you develop a space elevator. It's called sequences. It's quite a good technical note, and you could look at that.
All right, thank you very much. There is a little discussion going on in the chat in regards to using the Apophis that is going to approach the Earth in 2029 as a apex anchor. And there's a couple of people who are responding to that, so there's a little lively discussion going on. Perhaps you'd like to comment.
The original idea by Brad Edwards and probably Jerome Pearson and a few other people was we would use a large asteroid as the apex anchor. Uh, in my mind, as somebody who's taught orbits and a whole bunch of other stuff, it's just too hard. You first got to slow it down, and then you got to time it to the right place, and then you got to have the tether out there at the right time, and then you've got to connect it. And then after all that trouble, you still don't have a smart apex anchor. You still don't have reel in, reel out capability, and you don't have thruster capability, which would then moderate the dynamics of the tether. So even if you could do a asteroid as the apex anchor, I'm not sure it's what you want. The alternate, and I like this better. Now, this is Pete Swan's view. When somebody decides to give a space elevator team $1 billion to go design and start building, we'll come up with some final answers. But right now we have preliminary answers. So my preliminary answer is let's go to geosynchronous. And as we go past geosynchronous and raise the upper end, we attach derelict geosynchronous satellites. It does two things. One is it cleans up the geo arc, and it also gives us a mass at the end of the tether. So I believe we can clean up the geosynchronous orbit and pick up all those big geosynchronous satellites, put them together in a net bag, and use them as a mass. But then we also have thrusters in each one of those satellites. We have solar power capability, and we add the computer to it, and we can figure out what we want to do with it. So I really like the idea of scavenging old dead satellites to make it work. But that's Pete's idea. We can do all kinds of things.
Okay, and I have one last sort of comment question. Can you put the USS Voyager in space is less than 5 years, so that enables space exploration, maybe a 5-year mission, I believe is the
Hey,
question.
well, I agree with you completely. I think it's a brilliant idea. We should do that. Actually, just to add to the humor, there's an organization called the 100-Year Starship, and the idea is that humanity within 100 years would actually send people to the next star. And they're working on that. And I've gone to 2 conferences, and one of my papers at the conference was building the starship at the end of the space elevator. And I believe that's a viable solution. You can bring large masses up and you can assemble them at the apex anchor. Now, the beauty is that at the apex anchor at 100,000 kilometers, you have an outward force. So literally, when you put a glass down, the water would stay in the glass, or if you put a screwdriver down, it would stay where you put it. So you literally could build the Voyager out there and go to the next star system. And I gave a paper on that. So I agree with you, Paul. That's a great idea.
All right, and one last comment regarding your previous answer. How would you move an old geosatellite? Because they are derelict and they usually don't have any fuel left on the satellite. So how would you move?
Aha. You got to keep up with everything going on. They just had a successful thing. Now I'm naming a company. I think it was Northrop Grumman. Just had a successful revitalization of a geosynchronous satellite by sticking a robotic rocket engine in the old rocket nozzle, and therefore you have outside communications capability, and you've now able to move the geosynchronous satellite to where it was supposed to be. It had drifted away. So now they moved it. That was a successful mission just in the last week. So I believe they just showed us how to do exactly that.
Great. So we've come to the end of our session for today. I want to thank Dr. Pete Swan for giving us that very detailed presentation. And just as a reminder, if you didn't get an opportunity, we do have what we consider the full presentation here in this download pod. Just highlight it and click download. It does contain some additional information than what was talked about today. Now, please stay in touch with us. We are a member-driven volunteer organization, and if that is our main website, www.isec.org, you are able to click over there at that link, and that will take you directly to our website. Make sure you scroll down to the bottom to sign up for the newsletter. We'd love for you to keep in contact. And if you would like to, we have yearly membership. It's very modest, as you can see. And the Join Now button, go ahead and click that, and you'll be taken right to the page where you can actually join ISEC. And as a surprise, our next webinar will be May 29th at 1 p.m. UTC, which is Coordinated Universal Time, basically Greenwich Mean Time. You can go to timeanddate.com if you'd like to see the time in your time zone, because I know we have a number of people from all over the globe here, so we put everything in the Coordinated Universal Time there. The next webinar will be on materials with Adrian Nixon, so make sure you save that date, Friday, May 29th, 1 p.m. UTC. Go ahead and click the Register Today button. That'll take you right to our registration form, and we hope to see you then. Thank you so much, everybody. Thank you, Dr. Swan, and thank you, everyone here, for sharing your time with us. We are recording, and we'll make sure that we get the recording link up on the website. Thanks, everyone. Have a good rest of your day.